Morning friends. So today's lecture we will have a little bit of an idea of what we do to sludge. The primary treatment results in your influent getting screened of all the big particles. No very big particle, no grit and all this such things are removed. Whatever is the biomass that is generated there, whatever is the treatment of the screens, this is a biomass. That biomass is going to be further treated and you will be using some method to generate either biogas or other things depending on the requirement of the community or depending on the plant design. But what you get from the secondary treatment processes, especially what do we call the secondary treatment processes? All the processes that use some biological agents for reducing. Primary treatment plants use mechanical means as the prime mover or prime thing which does the work. In secondary treatment, you have the anaerobic or aerobic or bacteria to take care of that. The problem is I am not able to remember the spelling when I want to do it at a short notice. So I will not trouble myself too much on that, and you will understand what I mean by that word. So it is a bacteria which lives both in aerobic and anaerobic conditions. So that's about the secondary treatment, and the output of a secondary treatment will have lot of suspended material which has to be settled, and you will also have to treat it because that will have a lot of pathogens also in the process. That is the effluent, whatever the liquid that goes on, that is good, that is clear. However, the sludge, what is produced, that is not going to be very clean. So we are going to look at it. So we were talking yesterday about the activated sludge process. ASP in this case is activated sludge process. So we need to clarify the effluent of ASP. Not only that, we will also be requiring to handle the sludge. So here is a sludge thickener, the working of a sludge thickener. In fact, this is the first Indian video which I really felt was good.
Hello and welcome. In this video we will see how a thickener works. Feed enters tangentially into the feed well, which is then fed to the thickener. Solids start settling down. The scrappers of rotating weights scrap the solids towards the overflow. The liquid component rises to the upper part of the thickener to flow into the overflow line. The feed well is sized adequately to take care of the agent contracting in the feed slide. The deaerated and flocculated feed is then discharged through the end of the gap formed between the feed well and the further plate is secreted to velocity into the main body of the thickener.
This video is directed by Himanshu Srivastava, Department of Wood and Mineral Engineering, Indian School of Mines, Dhanbad, India.
Okay, basically if you have a look at this video, unfortunately I don't have a method to scroll the video and show. You saw a huge tank that looked much like your your trickling filter. So here you have a small basin in the top. Everywhere the feed is from the center. So where it will slow down the rate so that it enters the. Sorry?
It will come from the side, enter the tank.
The feed is 1 minute. I wish there was a pause button. Okay, there is a pause button, but there's no. Oh, here it is. Okay, here we go. So now you see, so it doesn't enter from the side. Basically, it enters from the center. The feed comes in this. Here it's called a feed well. So the feed well, it distributes the water or the influent. The influent is made sufficiently slow so that it doesn't disturb too much the condition inside the tank. So what happens here, the influent goes in, okay, this influent is heavy because it's carrying some sludge also. So once it goes in and the sludge starts, what is being carried is settling down, water gets lighter and it goes up. So this is what is in the green color, okay. So here this drive actually is pushing the sludge towards the center. This rakes, it just moves the sludge towards the center, and here this is called as the underflow. This is the place where the sludge is coming out. The sludge comes out through this arrangement. Okay, essentially there's an opening in the middle. So on the side you will have a weir. This overflows out into this place, and this will be clarified water. This will be clarified water, and yeah, what is the green is the rising water. What do you mean by rising water? When the water is not carrying any material, any colloidal material or any suspended material, it automatically gets lighter. So it is going up. The suspended material comes down. So whatever is given in orange here, these are all the substances which settle down. Okay. So this is much like yesterday you saw in that video, the water which was overflowing over the weir. It was clear. Okay. So this is the water which you get, which will overflow into this arrangement in the side. Okay. Any other question you have on this? Okay. So basically these are the design parameters: the weir overflow rate, solid loading rate, what was coming in the middle, and of course you also have the underflow removal rate, which will also come into the picture, and detention period, which is the time which it will take for ensuring that the process is efficient. If you are making it very small, detention period is going to be less, but the quality of the effluent is going to be much lesser. So all this solid loading rate means the amount of solids which come into the weir should have a particular concentration for efficiency of the operation. You cannot operate these anaerobic systems, which are actually quite slow in themselves, at variable loading rates. What do we mean by this? It means like, suppose you are on a road, if you want to go faster, just press the accelerator, immediately you are able to go fast in a car or retard it. Here the entire process takes sometimes, anaerobic digestion takes 28 days, and certain detention periods were 24 days, like in the 24 hours in the oxidation pond. So that 24-hour cycle, if something is there, it has to take the 24 hours. But if you are suddenly changing a parameter, that shock loading cannot be handled by any of these systems. Okay, so the actual design parameters are there in the video at the end. Okay, what I was talking about. It's a very clear video of all the design parameters, and I'm going to go in for some of the sludge drying techniques. So whatever goes out is the underflow which goes out is called sludge. It will be a slimy mass, clay sort in nature, and it's very difficult to dry it. If you notice, you will find it very difficult to squeeze out water from a clay sample. The reason is the water is held in place. The water is being held in place because of intermolecular forces also. So you'll see some of the ways sludge is being dried. WWTP is wastewater treatment plant. These are solar drying. using screws. They also got rubbers. They also can squeeze a little bit of water out of the sludge.
demo system begins.
Okay. So what did you see in this? Sorry? Sludge is dried. Okay. What do you think are the problems in drying sludge?
In this project,
Yes. Or in general also you can put it.
this one doesn't work in all the seasons.
Sorry?
The effect of the seasons will be there.
Okay. Then?
In consumption of electricity is more.
Why is consumption of electricity more in this? Why do you say that consumption of electricity is there at all?
Exhaust fans,
Okay,
flow of air,
okay,
and then only they use the flanges for removing as well as keeping it.
okay. Yesterday, okay, no, not yesterday. Okay, in the video which you are going to have as your flipped classroom, in that one you will have a. They will also dry this mass. In US, this is in China. In US, they have a norm that if suppose it is going to be something which is going to be handled by humans, that is, all the waste which comes out, all the sludge which comes out of the treatment is being that is, they initially they used it as landfill and only for manuring the hay. That is, whatever animals are going to consume, only they could use it. But to make it usable or fit for humans to come in contact with, and also for fertilizing the plants which will be food crop for humans, they had to make the biomass, whatever they get out, or the dried sludge, 100% pathogen free. In this one, I don't know whether it will be the amount of pathogens which are present in it is not mentioned. There they got 95% pathogen free. It means pathogens are harmful bacteria, virus, whatever. So here we don't know about that, but there what it is, they again heated the whole thing, so that they heated it to very high temperatures to ensure that it is fully sterile. Now in this case, so whatever they used here, it was being used there also. This is just a point. You are right. There is a lot of energy which is being used. The other methods would be like, putting it in a centrifuge. Okay, centrifuge is like your spin dryer. Putting it in a centrifuge and then getting it dried, or stuff like that. In the other one is there's a vacuum drying bed. I will just go through that. But in any case, basically handling sludge is it's very difficult. basically, if you see here, you apply you have a sand layer, and that you put your slurry, and then you can actually you can have a system to vacuum out the water from bottom. Okay, so this might be having much more impact on the cost. What?
Something similar to pressure pressure.
Sort of. So, but which is better now? The previous one used sun. It also had some screws. It also had to have some mechanisms to. Solar seems more attractive. Okay. So essentially, end of the day, so they may even heat this up to 800 degrees Celsius, like what they did in some of the processes. Water is definitely going to go. What is going to remain is only ash. But to heat to 800 degrees Celsius, can you imagine what 800 degrees Celsius is? Darn hot. Okay, and that will come as ash. It's coming out as fine powder. So we don't know which is going to be the best, which is going to be the most energy efficient. But end of the day, we still need to do it. Okay. So I just have one more thing which I will say I find interesting. Okay, in terms of this oil and grease separation, what you're talking about there. So you just have a look at this one. Since we talked a lot about this oil and grease separation, I mean we didn't do anything about that, right? Equalization tank is required when the flow rate is going to be different. Concentration of the influent, if it is different, we need to equalize it. Basically, what happens when you want to remove oil and greases, you aerate it and try to float off the oil to the top, and then you will take the other liquor, the effluent. I mean, whatever is the influent of oil and grease, you just take it from the bottom. Sometimes you can have a U-trap also. So what happens in a U-trap? The water which is above the U, it will stay there, and you can just draw water from the bottom. So oil and grease traps generally work on this principle, because oil is lighter, it will always tend to float above the water. So you might try to break it up with some detergents and cause it to, if as you require, depending on the nature. If suppose it's very thick, greasy, like your motor grease and all that, you will have to do some. You will have to use some surfactants to make it better. Okay, surfactants act only on the surface of the fluid. Then whatever is on top, you can just scum it. It will be scum which you can just float it and remove it. Okay, discarding this grease is very difficult. We'll just have a short break. Okay, then we will continue on. We'll have one short video on the thickener design. All the design parameters are going to come out beautifully in this video. Here we go. Just 1 minute please. I have to increase the volume. Right. This one
The underflow. The second way is over the overflow
I'm
weir.
just starting.
The purpose of this video is to help you better understand the function of a clarifier and start you on your path towards effective clarifier operation. The purpose of a wastewater treatment clarifier is to slow the water down enough such that suspended particles can be separated out by the force of gravity. Mixed liquor, typically from aeration tanks, enters through a centrally located feed pipe. From there, the flow has two ways out. First, settled sludge leaves through another centrally located pipe at the bottom of the clarifier and is recycled back into the system or wasted. This is the underflow. The second way is over the overflow weir. In a properly functioning clarifier, overflow water should look very clear. Finally, grease, oil, and other floating material is removed by a skimmer on the surface. Without going into too much detail, some other important components of a circular clarifier include the rake arms, an energy dissipating inlet, the drive mechanism, a feed well, and a density current baffle. To review, particles, represented by our bug here, enter the clarifier suspended in the water. As they enter the clarifier, energy is effectively dissipated, allowing the bug, which is more dense than water, to slowly sink, while the water eventually makes its way to the top of the tank and over the weir. Pretty simple, right? Well, a lot of work goes into making sure that a clarifier functions correctly. And one powerful tool which can help with successful and effective clarifier operation is the state point or state point analysis. Let's go through what the state point diagram is and what it represents. The state point diagram consists of a horizontal axis, which represents the solid's concentration, X, measured in grams per liter. The vertical axis represents the solid's flux, G, measured in kilograms per meter squared hour. In this case, the solid's flux is the mass of solids passing through the clarifier in 1 hour, normalized to 1 square meter of clarifier area. Now that was a mouthful. Let's try and simplify it. Imagine a tiny clarifier with a surface area of only 1 square meter. The flux in this case would be equal to the total mass of solids passing through the clarifier in 1 hour. So if 1 kilogram of mass were to pass through in 1 hour, the flux would be 1 kilogram per meter squared hour. Now if the surface area of the tiny clarifier was doubled, but the same mass of solids passed through in the same amount of time, the solid's flux would be half. Why? Because it is normalized to 1 square meter of clarifier area. The amount of solids going through the clarifier didn't change, but the amount going through 1 square meter did, by half. By using flux, one can compare clarifiers of different sizes and loads on an equal basis. Now that we've covered both axes of the diagram, let's get to the 3 main components. The first component is the settling curve. This curve is developed by performing velocity settling tests at various concentrations of mixed liquor on site. However, empirical equations based on the sludge volume index, SVI, have been developed and are plenty accurate for using in deriving this curve. A smaller SVI, which represents faster settling, results in a larger settling curve. A higher SVI, which represents slower settling, results in a smaller settling curve. So what does it matter if the curve is larger or smaller? Well, we'll find that out in a minute. But now that we know that SVI is important in determining the settling curve, how do we determine the SVI? and what causes it to change? Well, the SVI can be determined by performing a settleometer test. Also, if you can, use a diluted sample to determine your SVI. This will allow for more accurate results, especially when the SVI is higher. SVI can be affected by a number of things. Almost all activated sludge develops some filamentous bacteria. However, sometimes the quantity of filamentous bacteria becomes abundant such that it settles poorly due to bridging of the floc. As a solution to this, some treatment plants have installed systems which allow them to dose chlorine into the recycle flow, which can significantly reduce the filamentous bacteria. Other process hiccups and influent contamination can also affect the SVI. The second component of the state point diagram is the overflow line. This line represents the flow through the clarifier. As the mixed liquid concentration increases, the flux increases also. The slope of this line represents the surface overflow rate, or SOR, which can be determined by dividing the influent flow by the clarifier surface area. It is important to remember that this line can be adjusted by changing the influent flow rate. A higher influent flow rate results in a steeper slope up. A lower influent flow rate results in a flatter slope. The third and final component of the state point diagram is the underflow line. The y-intercept of this line represents the solid's loading rate, or SLR. The x-intercept of this line represents the expected underflow concentration. The slope represents the solid's underflow rate, or SUR, which is calculated by dividing the RAS flow by the clarifier surface area. This line can be adjusted in two ways. First, by changing the RAS rate, you can affect the slope. A higher RAS rate will result in a steeper slope down. A lower RAS rate will result in a flatter slope. Also, the location of this line can be adjusted by changing the solid's concentration entering the clarifier. A higher concentration moves the line away from the origin, with the opposite occurring with a lower concentration. Putting all the pieces together, we have our full state point diagram. So, how do we use it? We start by defining the actual state point. This is the point where the overflow rate line and the underflow rate line intersect. To ensure proper clarification, we want to make sure that this line falls underneath the settling curve. If this point falls above the settling curve, the clarifier is failing in clarification. In other words, the solids entering the clarifier don't have enough time to settle before going over the effluent weir. This could be caused by increased flows, not enough RAS flow, a high SVI, or a combination of any of them. It is not a good place to be. At this point, the clarifier is not doing its job at all. However, getting the state point under the curve isn't the only goal. In order to ensure proper thickening of the sludge, we want to make sure that the entire underflow rate line to the right of the state point falls under the settling curve as well. If the state point is under the curve, but the entire underflow rate line isn't, the clarifier is failing in thickening. This means that sludge is settling in the clarifier, but isn't being removed fast enough. Under these conditions, the sludge blanket would rise in the clarifier until solids are passing over the weir. Thickening failure, like clarification failure, can be caused by high flows, low RAS, high SVI, or any combination. So if either of these scenarios should occur, and you were to fail in thickening or clarification, there is some good news. The system will eventually fix itself. How? Well, if solids are passing over the weir, the concentration of the system will decrease. And as we've already covered, a lower mixed liquid concentration will move the underflow line back towards the origin and eventually under the settling curve. The bad news is, if this happens, you probably just violated your permit. So the goal is to avoid either types of failure. Let's take a look at some real-world scenarios now, where the state point diagram can help you determine what actions you can take as an operator. For this exercise, we're going to use an actual state point model. Let me bring it up. This is one version of an interactive state point diagram that can be used as a tool in clarifier operation. As you can see, this model has three methods for developing settling curves. The first is based on actual measured clarifier characteristics. The second is an approximation developed by Dr. Glenn Deiger. The third is a modification of the Deiger model called the Deiger-Roper. Let's simplify things and clear some values out of the other models and use just the Deiger model only. The diagram model allows you to construct an approximate settling curve based on the SVI. We're going to assume that we have some decent settling sludge here, coming in with an SVI of 250. Let's make the clarifier diameter 80 feet and specify that only one is in service. For this scenario, let's have everything going smoothly with an influent flow of 3 mgd, a RAS of 50% of the influent flow, and a mixed liquor concentration of 2,500 milligrams per liter or 2.5 grams per liter. Let's clear the second state point values now so we can focus on our single state point. And as you probably noticed, this model adjusts the graph automatically and immediately, allowing us to quickly evaluate how things are going. Well, we see that in this case things are going quite well. Both the state point and the underflow line fall under the settling curve. Man, life is good. The sun is shining, birds are chirping, and the air smells fresh. Well, as fresh as a wastewater plant has to offer. But just like any rainstorm can ruin a perfect day, it can also ruin your smoothly operating clarifier. So it's a rainstorm. Hits your system and the flows begin to rise. Before you know it, your influent flow has risen to 4 mgd and your RAS pumps don't automatically adjust with the flow. For this, we need to override the RAS rate. We see that 50% of 3 mgd is 1.5 mgd of RAS. Now we need to enter in the value in gallons per minute in the override box down here, which conveniently gives us the conversions to mgd. And because we're really smart, we know that 1.5 mgd is 1,045 gallons per minute. So we can enter that in here, and it overrides up here above. And now we can change our flow to 4 mgd. And as you can see, our state point stays under the curve, but our underflow line doesn't. We know we are going to fail in thickening. So what can we do? Well, let's see. Say we actually have a little bit more capacity in our RAS pumps and can turn those up to 2 mgd. Well, does it help? Yep. As we discussed, increasing the RAS flow results in a steeper underflow rate line, and we're back in good shape. Good job. Crisis averted. But what would happen if flows continued to rise? Let's say to 5 mgd. Well, in that case, we'd be failing in clarification as well as in thickening. Also, as mentioned, we've already maxed out our RAS pumps, so we can't pump any more out of the clarifier. In this scenario, there are two options. First, if the flow increase can be predicted well in advance, there exists the option to preemptively waste solids to reduce the mixed liquor concentration. In this case, if the mixed liquor concentration was preemptively reduced to 2.2 grams per liter, we see that we'd be back in the safe shelter of the settling curve. However, this is not a realistic approach to dealing with unexpected high flow events that occur from time to time. Typically, the only other option available in this scenario is dosing your RAS line with some chlorine. A quick dose of chlorine in the RAS can attack the filamentous bacteria and lower the SVI. If the chlorine dose was able to drop the SVI down to 200, we'd find ourselves back in the safe zone. However, this option is only available to treatment facilities with the proper equipment installed. So now we've seen some ways to avoid failure, but the state point diagram can also help optimize clarifier operation, not just prevent problems. Let's go back to our nice, properly functioning clarifier. The SVI is back to 250, the flow is 3 mgd with the RAS running at 50% or 1.5 mgd, and this time let's say that we've wasted.
With your permission, I'll pause this. Reason is, it might not interest you, it's only a very short portion which is remaining, but here, what are the things which you saw? You have a diagram called Sludge Volume Index, SVI, this yellow color curve. So this is going to tell you how sludge is going to settle and thicken. So it is a relationship between a volume of sludge and weight thickening. Now you have two lines here. One tells you how the what is coming in and how it is going out. So this line, and then you are finding where the state, where it is going to be present. So you can change the profile by modifying chlorine. That is, it means that you are killing some of the bacteria which could be there, basically what we saw a little earlier, the filamentous bacteria which can cause troubles in settling. Or so these are some of the ways by which you can play around, changing, like once you know the inflow is more, so what can we do something to the outflow? to make sure that thickening does take place. So this is what we are doing. But I don't know whether we are going to have such a good system in India. But look at all the parameters which are there. See the area of the thickener, that plays a lot of role, because because larger the area, actually what happens is the periphery overflow rate can be varied. You can pump the water at a particular rate. Suppose you are having a larger length, at a slow rate itself, more volume of water is going to go over the weir. If you are having a very small one, your overflow weir is going to be so much smaller. So all these are parameters which you can, and then the underflow rate, the rate at which you draw out the sludge, that also is going to play a very important role. Okay. So that's what we call as the expected underflow rate. Then again you saw about the solid flux, like how much of solids are going to come into the clarifier per meter square. So that's called flux, much like your magnetic flux, which we saw about in your, if you saw it in physics probably, magnetic flux. Yes, and solid concentration, amount of solids which are coming in. See, suppose you are having solid concentration might be fixed for a particular duration. So that if the concentration is more for a particular area, flux is also going to be that much higher. Okay. So probably yes. So these are the references which we have got in this particular lecture, and thank you for your patience. And I hope you found it useful in the sense that all the calculations which are going to be done, this sort of calculation is going to be done in all the wastewater processes. Any water process you take, they'll have certain parameters which are absolutely binding. Like for in this thickener, what are the parameters which we saw? The overflow rate, weir overflow rate, the influent coming rate, and the rate at which you are drawing out the material settle, and also your contact period or the detention time. So these are going to be common for almost all the unit processes what you are going to take up. Okay. So thank you very much, and we'll be